Okay, so he just pretty much said what I was about to say, so I have to turn on thinking mode. Maybe let me add a few words to this. We can use telescopes to watch across very large distances to look back into the early universe. But in the early universe, matter was much more densely concentrated, which brings us to higher energies. So these two things naturally fit together. So I find the question a little oddly phrased. Like if you say, do the large distances and the small distances disagree with each other? We actually use them both together necessarily. So maybe let me illustrate where the problem actually comes from. I think it's fairly easy to see if you think about what you know about quantum physics. If we have a particle that goes through a double slit, we often say this particle's in two places at once.
Yeah, a lot of people have at least heard of the double slit experiment, right? That according to quantum mechanics, I think it's like a particle becomes a wave and then it's in superposition, so it's in two position. It's in literally two physical locations simultaneously, which is one of the most fascinating, mind-boggling aspects of quantum mechanics, as there are many others, of course, right?
So typically that could be an electron, for example. And we know that these electrons have mass, so they must have a gravitational field. But we don't know what happens with the gravitational field because in Einstein's theory, the gravitational field doesn't have quantum properties. It can't be in two places at once. So this is why we say we don't know how to put
So
the
there's a gravity field, but it's not quantum under Einstein's theory, but it seems like the way it works is that it is quantum. So they have the relativity part, but they don't know how to make the relativity and quantum parts match mathematically, even though they use both types of equations to work to actually solve problems on a regular basis. They just don't know why that is or how it's working or how to make these theories compatible in a way that you can use one theory to figure out every kind of measurement, whether it's a small object or a large object, like she was saying, right?
these things together, like a theory for space and time. We do have one, that's Einstein's theory. And then we do have a theory for the quantum particles, but they don't like to cooperate. And this is the problem. And we're still trying to figure out how
So
to
you
combine
can't get quantum mechanics to work with time with Einstein's theory of time space either. I forgot that aspect.
these two things. And there are two very important areas where that
And philosophically, not scientifically, we can talk about whether space and time are actually things. And even like scientifically speaking, if I understand correctly, time is not a linear thing, and it's connected to space in that more or less time can pass depending on how far you travel through space, if I understand that correctly. But also, like both philosophically and scientifically, time is not necessarily linear. That's kind of our relativist perspective on it, which is one of the fascinating reasons that philosophy of science can be so fascinating, right?
becomes relevant. One is the beginning of the universe. Like if we go back in time to times even earlier than what we can look at right now, then at some point the quantum properties of space and time themselves should become important. And we don't have the maths for this, so we just don't know what to do. And the other
Yeah,
situation,
if I understand correctly, physicists know physicists know in detail mathematically what happened in the Big Bang during the Big Bang after the first 10 to the power of negative 10 to the power of 37 seconds, so like an unbelievably small amount of time, but they know what happened mathematically after that point. But she's saying that like they're kind of clueless so far about how the hell to figure out what happened at the exact moment of the Big Bang of the universe.
is what's going on inside black holes. No one really thinks that there actually is a singularity, it's probably something else, but then what? And then, of course, there's this issue with the double
That's
slit.
interesting too, because we all hear that black holes have their own singularity, right? But it seems like possibly more recently physicists have figured out that they actually don't. They have possibly something similar to a singularity, something that looks like it but is actually not that. It makes you think about all those fascinating science fiction movies like Interstellar, for example, too. I mean, spoiler alert, it came out a long time ago, but basically they find out that if you go into a black hole, you can just physically travel forward and backward in time in order to basically subtly alter events in the real world in order to cause the outcome that will lead to you going into this black hole in order to do these subtle things to affect time, and it becomes a time loop, which is obviously fascinating too, right?
Which we really want